thank the organizers for putting this together. Okay, 10 minutes, wrap mode. Today I will talk about multi to one-dimensional and semi-discrete screening, or monopolist problem, or principal agent problem. This is a joint work with my supervisor, Brandon Pass. So a monopolist or a company offers goods of type Y with the production cost C of Y. And we consider the set X to be the set of buyers types with distribution mu. A buyer of type X gets utility Bxy minus V of Y at price V of Y if they choose to purchase the product Y, where B is the preference function. It tells us how much buyer of type X values or needs product of type Y. We assume that consumers will behave in their optimal interest, which means that they're going to choose the product that maximizes their utility. And of course, they have the option to not buy anything, and it's described by purchasing product Y0 for price equals to 0. And the monopolist goal is to maximize the profit, the difference between the price and the cost of production, over the pricing functions. So we need to put find the optimal pricing function V that maximizes the profit. And the challenge here is that V must indirectly screen or distinguish buyer types using only prices, which means we don't know individuals' types, but rather we just know their distribution. Okay, there have been a lot of work done in this area. When X and Y are both one-dimensional, things are easy. The problem reduces to solving some ODE, or we can use optimal control methods to use it under the Spence-Merle's condition. In the multidimensional case, things get dramatically more complicated. And multiple phenomena starts to appear, like exclusion and bunching. It have been studied a lot, and I think Dr. McCann will cover in details on Friday's talk. And there have been some work that focused on the multi to one-dimensional case. So in our model, we take X to be the unit square, and mu is absolutely continuous. And we take the two cases for the products. It's either finite set of product types or an interval, continuous interval. The preference function is going to be the dot product between X and points on some increasing and convex curve of Y. And the cost, it's going to be convex and increasing in Y. And C of 0, 0 now, it's the opt-out option or the not purchase option, and its cost of production is 0. So if we take nu to be the YV, YV is the optimal product that each consumer will choose. If we take nu to be YV push forward mu, that would give us the distribution of products that are actually purchased. And then YV will solve the optimal transport problem matching mu to this nu. So in the monopolist problem, nu is endogenous, it's unknown. It depends on V. So for each pricing V, the products purchased will be different. So understanding the structure of the optimal map will help in both problems. And so if we can understand or characterize the geometry of the level sets of this optimal map, this will simplify the study of both problem, now in particular the monopolist. So we'll introduce this structural property that will guarantees this characterization. So we start with a finite menu Y, and for a pricing function V, we define this region, Xi of V. It's the set of consumers that prefer product Yi over Yi plus 1. And we define nestedness. We say V is nestedness or YV is nestedness, is nested. If xi of V is subset of xi plus 1. What that will give us is that the regions xi of agents choosing products yi are going to be ordered, and the boundary between them will never intersect. And if a buyer prefers product yi over yi plus 1, that means they're going to prefer yj over yj plus 1 for all j greater than I. And in 1D, this reduces to monotonicity of YV. And we introduce this as a generalization for monotonicity in the case of multi-dimension. And it even can be, in some sense, the analog of continuity for the semi-discrete problem. So this is a semi-discrete analog of nestedness that was introduced in Schiapuri, Makan, and Pass on optimal transport between two continuous measures. So we see an example here. An unnested V, for example, will give us these regions, xi purchasing yi, and you can see that the boundary would intersect. That's a general semi-discrete model. In a nested V, you can see not only the boundary of xi don't intersect, xi is going to be adjacent to xi plus 1, and xi plus 1 is going to be adjacent to xi plus 2. So we have ordering or sense of monotonicity. So under some technical but necessary convexity and regularity assumptions, any optimal pricing function V for the monopolist problem is going to be discretely nested when y is discrete. That will give us the allocation why V is going to be ordered and the boundary won't intersect. And the incentive constraints decouple. That means the problem is going to reduce and boil down to a system of equations where each equation depends on one variable. And that makes the computation complexity linear in N, which is a huge gain over traditional screening methods. And in some cases, for example, when mu is uniform, we can find the solution explicitly. Capital F is going to be the curve, and we're taking points over that curve. Small f is the density for mu. Yeah. Okay, so here, this case, it's nested. This is the explicit solution. If you can see that the boundary does not intersect with other boundaries. In the other case where nestedness fails, you can see the level curves actually intersect each other. Yeah. Yes, yes. So our conditions actually gives us a threshold for this case where nestedness fails. So 1/3, it's like the maximum convexity that we can do. Yeah. And so when the menu y becomes a continuous interval, so let's say we take the finite set y and it converges to cover the whole interval, the discrete layers that we saw, xi, will converge to level curves indexed by y. And we prove that they will stay ordered and non-intersecting. And that's the definition of continuous nestedness that was introduced in Schiapuri, Makan, and Pass paper. So under the same assumption, there exists a continuous nested optimal assignment for the monopolist problem. So the level sets don't intersect, and it gives us a continuous allocation, which is not the usual case when you have matching different dimensions. Discontinuity is like the usual case, but here you will get a continuous. So we proved that discretely nested solution will converge to a continuous nested solution as the discrete y goes to the interval y. And we get a continuous solution for the monopolist problem in the continuous y. And it's globally ordered, as we mentioned. So we get discretely nested. That simplifies the computation a lot, and we get a continuous solution, which is the advancement and regularity section. Thank you very much for listening.